Hello student, last lecture we learned about the moment of inertia and we also find out the formula for moment of inertia. I is equal to summation of mi ri square. I start from 1 to n numbers. Okay, in this lecture we learn expression for kinetic energy of a rotating body. So when body is rotate, then it's find out kinetic energy. Now see this figure. When any shape of the body, the rigid body, is rotated with a axis of a rotating axis with a constant angular velocity omega, and then its mass distribution is m1, m2 up to mn numbers of particles, and then is the r1, r2 and rn is the distance from the axis of rotation to each individual mass. Okay, so here we find out the kinetic energy of the body. So consider a rigid body is rotating about an axis, passing through it and perpendicular to its plane. So let us find the kinetic energy of the rigid body. The rigid body is made up of a number of particles as the body rotates about axis. Each constituent particle moves in a circular path having radius equal to its distance from the center, that is the axis. The kinetic energy of a rigid body is equal to the sum of kinetic energy of constituent particles. So kinetic energy is equal to kinetic energy of first particle plus kinetic energy of second particle plus kinetic energy of third particle up to kinetic energy of n particles. So we get here total kinetic energy. So now find out the velocity, linear velocity first. Let v1, v2, v3 up to v1, vn particles, velocities of the particles, and we know v is equal to r omega is the relation between linear velocity and angular velocity. V is equal to r omega. So for each particle's velocity is v1 is equal to r1 omega, v2 is equal to r2 omega. Here not omega 1, omega 2 because omega is a constant. So v3 is equal to r3 omega and vn is equal to rn omega. So now kinetic energy for first particle is, because we know that total kinetic energy is equal to summation of all kinetic energy of all particles. So here for the first particle, kinetic energy is half mv square. Here m1 is mass of the first particle, v1 is the linear velocity of the first particle. So we get the formula kinetic energy for the first particle is equal to half m1 v1 square, and then we know that v1 is nothing but a r1 omega. So put up the value, then we get half m1 r1 omega square. So solving this equation we get half m1 r1 square omega square. We get a kinetic energy for the first particle, similarly for the second, third and up to n particles. So similarly kinetic energy for second particle is equal to half m2 r2 square omega square. Kinetic energy for the third particle is equal to half m3 r3 square omega square, and kinetic energy for the n particles is equal to half mn r square n omega square. So their total kinetic energy is equal to kinetic energy for the first particle plus kinetic energy of the second plus kinetic energy for the third plus up to kinetic energy for n particles. So kinetic energy is equal to half, put up the values for kinetic energies, then half m1 r1 square omega square plus half m2 r2 square omega square plus half m3 r3 square omega square plus up to half mn rn square omega square. Here constant term is omega square and half, because m1 and r1, m2 r2, m3 r3 up to mn rn square are different quantities. So here constant values are half omega square in bracket m1 r1 square plus m2 r2 square plus m3 r3 square plus up to mn rn square. So this is nothing but a summation of mi ri square numbers. So we put up here summation of mi ri square, and I start from 1 to n numbers, correct? So here write down I start from 1 to n numbers. So kinetic energy is equal to half omega square, and we know that the formula for summation of mi ri square, I is equal to 1 to n numbers. This is nothing but a I means moment of inertia of the rotating body. So I is equal to mi ri square. I is nothing but a start from 1 to n numbers. So we get kinetic energy means total kinetic energy is equal to half I omega square. Half I omega square, we get the kinetic energy of the particle rotating body. So SI unit for this kinetic energy is kg meter square, and dimension is m1 l2 t0. So this moment of inertia is significance and analogy with mass. So like mass in linear motion, moment of inertia plays the same role in rotational motion. Means linear motion, it's here in linear motion mass plays the same role in moment of inertia in rotational motion. Okay, second one, greater the mass, greater the force required for linear motion. Similarly, greater the moment of inertia, greater the torque required to rotate the body. And the next significant is in linear motion, inertia only depends upon mass, while in rotational motion, inertia depends on mass and its distribution. Okay, if we compare the linear and angular physical quantities, the analogy between inertia and moment of inertia will be established. Okay, so here analogous terms are F is equal to ma. We learned the formula for force is equal to mass into acceleration. Here similarly in rotational motion, tau is equal to I alpha. So here mass plays the role for here in rotational body is moment of inertia, correct? So we know that again formula for P is equal to me, momentum, linear momentum formula. And so in rotational motion, L is equal to I omega. Again here mass plays the role in a inertia, a moment of inertia in rotational motion, correct? So L is a rotational momentum. So L is equal to I omega. Then kinetic energy is half mv square. Here kinetic energy is half I omega square. Now our next point is parallel axis theorem. So now we also find out the formula for parallel axis theorem. So statement for the parallel axis theorem: the moment of inertia about any axis is equal to the sum of its moment of inertia about a parallel axis passing through its center of mass and the product of the mass of the body and square of the distance square of the perpendicular distance between the parallel axes. So this is the statement, and then we mathematically write the formula for parallax theorem. I naught, here I naught represent moment of inertia about an axis. IC is the moment of inertia. I means moment of inertia. MI is denoted I. So moment of inertia of a same body, moment of inertia of the body of center of mass, axis passing through the center of mass, and here M is the mass of the body and H is the perpendicular distance between parallel axes. Okay, so here let us see first figure. Here any rigid body of any shape, then here C point and O point represents the parallel axis. Both are parallel axis, rotational axis. It is the from the center and is the passing through from O point. Okay, so here distance between these 2 points is H, denoted by H. So now we prove the parallax theorem, then find a mathematical formula for parallax theorem. I naught is equal to IC plus MH square. Okay, so now in this figure here shows a two axis. So first axis from the center of mass, then here C, and second axis is parallel to the this axis is goes to the O point. Okay, so moment of inertia for center of mass is denoted by IC. So moment of inertia about an axis passing through the C point or center of mass, and I naught is the moment of inertia about an axis passing through a O point. Okay, and the distance between two axes is denoted by H, and D is the small mass of dm. Okay, is the any point. D is the any point and its mass is dm. Here small point dm. So distance of OD is denoted by R, and CD, this distance CD from the center C point to D point is R naught, and CN, the distance is X, and OC is H. Okay, so here considering a two axes. So figure shows these all points. Here MP and AB is the two parallel axis, rotating axis. Okay, now we solving this parallel theorem. So we get here some points. So we already know that OD means R, CD means R naught, CN means X, and OC means H. So formula for moment of inertia of the body passing through the O point, and moment of inertia of the body of passing axis passing through the C point. Okay, in center of mass point. So we write the formula for here moment of inertia. So I naught is equal to integration of R square dm, and IC is equal to integration of R naught square dm. So in O and D right angle triangle, so we'll again see the figure. O and D triangle is the right angle triangle. So OD square is equal to ON square plus DN square. Correct? So here putting all points in these values. So OD square, your OD means nothing but R, so R square. ON means OC plus CN, correct? OC plus, so CN square plus DN square. So OC square, OC means nothing but a H, so H square we are putting all. So once again here solving this bracket first and then putting the values, okay? So OC plus CN square means OC square plus CN square plus 2 OC plus CN plus DN square. We are mathematics solving this one bracket. So OC square plus CN square plus DN square plus 2 OC CN, correct? So OC square plus CD square. Here using the triangle CND, so CD square, we find out this value of this side. So CD square is nothing but a CN square plus DN square, correct? So here putting the value for CD square, correct? So CN square plus DN square is come from the triangle CND, right angle triangle CND. So we get here CD square plus 2 OC CN, correct? Now put up the values. So R square is equal to OC means H, so here H square plus CD means R naught. So put up the values R naught square plus 2. Again OC means H and CN means X. So multiplying dm, small dm on both sides, means here multiplying R square dm is equal to H square dm plus R naught square dm plus 2HX dm. Okay, so here integrating to both sides we get integration of R square dm plus integration of R naught square dm plus integration of H square dm plus integration of 2HX dm. Now here solving the integration. So integration of R square dm is nothing but a I naught, means moment of inertia of the axis passing through a O point, correct? And here R naught square dm is moment of inertia of the body passing through a center of mass plus H square is the constant term. So put up the outside from the integration. So H square integration of dm plus 2h, again h is the constant point, and integration of x dm. So here as C is the center of mass, the algebraic sum of moments about the center of mass is always 0. So here this term, here dm is 0. So putting here x dm is equal to 0, then we get here term is x dm is equal to whole term is 0, correct? So now remaining term is I naught is equal to IC plus h square integration of dm. Okay, so integration of dm means small mass of the particle. So here we adding, means summing all small particle mass of the small particle, then we get a mass of the whole body. So here we get integration of dm means m, means mass of the whole body. So I naught is equal to IC plus m h square is nothing but our formula. I naught is equal to IC plus m h square. We prove the parallel theorem axis.